wonderful to be here and talk about geothermal, a topic we couldn't cover yesterday, not yet enough. And I will speak about a topic that we totally forgot about yet. But before we start, I would like to introduce the Expo group, which is the Energy Simulation Chair group at ETH, which I'm heading. So you see several faces here that are part of that group. Not everyone could come, but I brought 3 students, and I will introduce them later on. We are collaborating worldwide with different industry partners, with people here in the room, and different universities. We also have graduate students that already joined the industry after doing their thesis with us. So yeah, it's wonderful. And also, I want to mention we are hiring. I'm looking for a field geologist. So if you're interested, or if you have someone interested, please contact me. So the topics we're working on are kind of twofold. We look into the exploration side. That's also part of the name of Expo. So exploring new fields, green fields, but also brown fields, because we still have an issue with drilling geothermal wells. They are not as productive as we would wish to. And also we look at the operational side. And there we look into efficiency and also safety. And this is related to scaling, to corrosion, to different issues we face once the geothermal plant is in operation. We work along different small projects. Last year I talked about the underwater drone. Just to mention here, you can look up my talk from last year online. We also look into temperature estimation of geothermal reservoirs. And we see a big mismatch between measured data and estimated data. So we try to be better here and improve the equations. And also we look into the evaluation of geothermal potential here, especially in Switzerland, but also in collaboration with other partners in different countries. Then we have a big study led by Anna. She's here in the room, and she has a poster. So please visit her to learn more about her experimental studies and numerical studies on clogging, on chemical precipitation in geothermal environments, close to the wells, but also in the reservoir. She can talk much better about that than I do. And currently I have a student, a master student, working on geochemical signatures in geothermal fluids. So we look into the distribution of different chemical properties in different countries and different enthalpy environments, and try to link them also to scaling. So we try to forecast what's the scaling potential and the risk here. On the other side, we also look into the efficiency of these geothermal operations. We see in high enthalpy systems, when we have these hot springs, that they change once the operation is in place and taking place for several years. We see a difference in chemistry and so on. So we have a PhD student working on that. And also Kevin and Sahart are here, sitting at the table having a poster. Please talk to them, visit them at their poster. They study the idea of replacing the water in the underground with CO2 and using CO2 as a working fluid. And it turns out to be much more efficient and a great idea to maybe consider in the future. And then we have a new project coming up, the Beach Project, and this is the topic of today. So we will explore new opportunities for geothermal heat storage. So we didn't talk about storage yet. We talked a lot about net zero, cutting down energy consumption, cutting down CO2 emissions. But, and it looks nice. I brought 2 statistics here from Canada. So that's natural gas consumption on the left side. And you see there are huge peaks, of course. This is in winter time, just starting right now. We need more gas to heat our buildings. And the general consumption is going down, which is nice, right? On the right side, you see the electricity consumption of Calgary's municipality buildings. Also, this electricity consumption is going down. That's a nice news. But also, there are some peaks. If we look into the peaks on the heating side using natural gas, it's an order of magnitude variation between summer and winter, right? We need a lot in winter, and in summer we are somehow fine with the temperatures around here. And if we zoom in, on the right side, you see statistics of one place, also in Canada, which is the heating demand over 1 year. And you see again this dip in the summer, where we don't need a lot of heating, but in wintertime we need a lot. and electricity demand is somehow stable with peaks over the day, right? So, and on the bottom side, you see another place, just randomly, it can be anywhere on the northern hemisphere, basically. Again, a lot of heating demand in the winter, low heating demand in the summertime, and you might realize this yellow, the yellow curve, which is the temperature, right? So we have high temperatures in summer, low temperatures in winter, and why couldn't we combine that? Wouldn't it be nice to use that excess heat that we have in the summer, so the high temperatures in the summer, to kind of store them, keep them, and to be able to use them in winter? And that's the idea that is shown on the right side. And at the bottom, you see energy providers, basically, and you see a small, very stable curve down here, the orange one, still small, but very stable and constant. This is geothermal energy. This is 24 hours, every day, year. It's available, right? And so how about we combine that and use geothermal energy as the stable base load that we have? So we have excess heat in the summer, not only by temperature, we could use additionally something like solar, but geothermal is available anyway. So how about we store this excess heat in the summertime and use it in the wintertime? This idea is not new. It's a concept of aquifer thermal energy storage. And just to give you an overview of where we stand with geothermal projects, we have these deep systems, fractured systems, EGS systems. We have geothermal heat production, like Sebastian just mentioned, right? These open hole systems, hydrothermal systems. And I did not put ever yet, right? So we have additional technologies here yet. This is an old graphic. So we are expanding on the right side, but we also have the left side, the buffering, right? The storage of heat. We can't put heat into the underground. There's a lot of space and time. And how about we also focus on the left side? So as I said, this idea is not new. Our friends in the Netherlands, they're using this since decades. They have currently 1,500 systems, or even more now, installed already. So the idea is that you have this excess heat in the summer, you store it in the underground, you extract during summer the cool from the underground and cool your buildings, and in wintertime it's vice versa. So you store your cool in the underground for the summer, and the heat that you store during summertime you use in winter for heating your buildings. So this is done in highly porous aquifers, in sandstone basically, and it works very well, state of the art. So we thought, how about we transfer this to Switzerland? And then the geologist came again, sorry. But the geologist said, yeah, very nice idea, but there's only a small part of the country where you can use that technology, which is the yellow part, what we call the Molesse Basin, which is full of sedimentary aquifers. But also 80% of the population live in that area, right? So there's a lot of kind of overlap of how to use these aquifers for groundwater, for drinking water. Us coming with the idea of storing heat in that area. So how about we also go beyond that and use the other parts of the country where also people live, actually. But the problem here is that we have fractured rocks. And this technology was never tested on fractured rocks. So this is the whole idea of our project. So it's a new technology of fractured thermal energy storage, not aquifer, but fractured, so it's FTES. And our project is called BEACH. It's the Bedretto Energy Storage and Circulation of Geothermal Energy. And also we heard, first, before we start a new technology and testing it, we need to understand the underground. So again, geologists, sorry for that. And we have a perfect underground lab for that. So ETH is owning a tunnel in southern Switzerland, which is a former transportation tunnel, let's say, for another railway tunnel. And it's not used anymore. So they're renting it out to us permanently. And we installed a lab, a geothermal lab, in this underground tunnel. The tunnel has a length of 5 kilometers in total. And right in the middle, at 2.5 kilometers, we installed a big cavity. You see pictures here, and you see small videos. You can watch the video by scanning the QR code. I will show it later again. A big cavity, we have wells in this lab. We are in a granite right now, a rotondo granite, and we installed several wells here. So we have 2 deep wells, which produce water if you open them. So they're artesian wells, two of them, 400 meters deep, so from the tunnel ground, it goes 400 meters diagonal into the underground, and we have 1.5 kilometers overburden. So basically, we are roughly at 2 kilometers depth in a real geothermal reservoir. We have, in addition to these deep wells, we have several monitoring wells, which you can think of an umbrella, which are around these wells, like 10 to 15 additional shallower wells around these two deep wells, which are fully equipped with anything you can wish for. If there's a wish we don't have yet, please tell me. But we have any sensor you can think of, from temperature, pressure, any geophysics, seismics, VSP, whatever you need to monitor the underground, we installed, and we did experiments throughout the past 5 to 6 years, and there are gigatons of data now. So we understand the reservoir, we monitor it, we know where the fractures are, we know what we are dealing with. The idea of the beach project is to use these two deep wells and circulate water. Like as you see here on a fracture at the surface that I found, you can see that the water is zipping through these fractures slowly, and we want to understand how fast the water can flow from one well to the other. And also not only the flow between the wells, but how about we let it rest for a while, because we talk about thermal energy storage, right? So the idea is always we have 4 phases. Okay, the colors are gone, never mind. We have 4 phases. We inject hot water, we let it rest, we produce the hot water to use it, and we let it rest the reservoir again. And then we start loading again. So because we are loading with a higher temperature than the reservoir, at least here in the Bedretto case, the temperature is going up, the blue curve. Okay, that's not working. No. Yeah. So you see the blue curve, slightly increasing temperature. That's the temperature recovery, basically, that we can gain once we load the system, right? And normally this operation process, these cycles are a full year. So in real case, it would be injection of 3 months, resting for 3 months. So you would load the system during the summer, maybe depends where you are, but maybe it would be July, August, September, where you load the system. Then you would let it rest. In wintertime, you can extract the heat for 3 months, and then you would let it rest again. This is the normal operation cycle. You can adapt to your climate, to whatever is available. There are different use case scenarios we can think of, and we will calculate also in our project. So Mahmoud, a colleague in our group, he did thousands of simulations to see what's actually the efficiency, how high can we go, and what's the dependence on different parameters. So he varied the depth, he varied the geothermal gradient, the permeability, also the injection, the mass flow rate, how fast do we inject, how fast do we extract, and also the thickness of the reservoir, and we're talking about fractures, right? So it's not a thickness of porous media, but thickness of fractures. Is it better if they are widely opened, or is it better if they're thin, but more of these fractures, right? We look into all these scenarios, and in the middle you see the Bedretto case, the blue one. It turned out to be, because we are in a still kind of shallow and cool environment, and it's our lab. We want to do first this test in our well-monitored environment. We turn out to have an efficiency roughly about 70%. This is already good, because we inject like 40 to 60 degrees into a 20 degrees reservoir. Of course, we will not gain temperature in this reservoir. But in real case scenarios later we will, and this is what the green dots here show. If we go deeper, if we go to higher geothermal gradients, we will have efficiency above 100%. So the project is made up of different phases. We have 1 to 3 phases a year and 1.5 years phases. We are right now at the end of phase 1. And what we basically did so far is the feasibility and economic studies. I can today present you a little bit on the modeling of the feasibility. After that, now we already started the experimental design, because we want to start experiments in December already. And we will execute the experiments. We have 2 different phases for that. First, we will only use 1 borehole. We will load 1 borehole and extract from that 1 borehole. And in the second phase, in the last 1.5 years, we would like to use both boreholes. So we will inject and load in 1 borehole and then extract from the other one. Along that, we have different industry partners joining us, and our goal is to have a market-ready technology at the end of this project, which is 4 years. we would like to hand over this technology to the industry, so we always work also on the rollout of the technology and the integration into the energy system, which is the yellow button here. So Tsubasa, our colleague, a postdoc, joined us last year, and he set up a model for first the Bedretto case, but then also a real case scenario. He combines the fracture network, which is very well known, which we will use, and where the boreholes target actually in the Bedretto lab. And he extracted data from this huge database that we have from 5 years of experiments running in this lab. He extracted the data that is useful for him to calibrate his models. And right now we are at the stage that the borehole test data fit his model data. And he could already run pre-experiment modeling studies. That's how we call it. So we started with different intervals, because also I told you the goal or the perfect scenario is that we have a full year of loading and extracting and resting. But for our experiments, we don't want to do an experiment for 1 year and then check, oh, sorry, this didn't work out, so we start over. So we will start with shorter experiments. And this is what we right now model to see what makes sense, what do we want to do, what is a good kind of balance between experimental time and also some efficiency we want to reach. So we started with intervals of 2 days, so 2 days of loading, 2 days of resting, 2 days of extraction and resting again, just also to see if our equipment works, if the wells can handle this, if the temperatures are still the same, to see what happens actually to our reservoir, up to the 90-day scenario, which would be the 3 months loading, 3 months resting, 3 months of production, and 3 months resting. And in the best case scenario, we already proved that the pre-proposal or pre-project models that showed this roughly 70% of heat recovery, we can rebuild here in our real case scenarios with the Bedretto data, which is quite good. Also, we model real case scenarios. So we already found an industry partner in northern Switzerland, and they are interested in this idea. They have excess heat, right? Where do we get this excess heat from? It's not only the sun and the warmth in the summertime, but also there are industry processes that have excess heat. Waste incineration plants, they produce heat all year round. So they want to get rid of that. If they can sell it, or if they probably can store it and use it for other purposes in wintertime, they would be happy. So we joined forces with that Schaffhausen real test site, and we talk to them. They give us real data from their operation, what they can probably provide as heat input and so on, and we model different scenarios again. But we see the deeper we go, of course, the heat recovery will be higher, because at the same time we not only store heat, but we also extract heat, right? It's at the same time that for example, the waste incineration plant provides basically 40 degrees of warm water. We inject it into the underground. There we have 70 degrees warm water. That's what you see in the small video. And then we also gain energy. We gain heat, and we can extract heat additionally to the storage. So that's also part of our project, that we want to bring this to the market. We want to show it's really possible to have real case scenarios here. So as I said, we would like to start with our experiments very soon. In December, we will have our first tests in the lab. We thought of 1-week cycles. That's the result of our models at the moment, that 1-week cycle is a good start. So we will load for 1 week, rest, produce for 1 week, and then let it rest again. And with ambient temperature. So in the tunnel, it's nice to work in the tunnel in wintertime because it is 17 to 18 degrees. It's warm, it's constant. There's a constant water flow in the tunnel, so we use that water that is available. It's easy, we will start and do our first experiments. For the later experiments, beginning of next year and throughout next year, we still think about the experimental design. Will we use a boiler to heat the water like some of you might have in the shower? Will we use a hot water tank? Will it be outside of the tunnel? Will it be inside of the tunnel? There are also security issues we have to think of, people working in the lab and being 2.5 kilometers beneath the mountain, basically, right? We have to think of their safety as well. So these are thoughts that are ongoing at the moment. So in conclusion, energy storage is still an unsolved problem worldwide, and we have to care about this. The subsurface is an Earth battery. It offers time and space that we can use. There's a state-of-the-art technology. We would like to bring it to the next stage of transferring it to fractured rocks. This can be done also in the Rocky Mountains, I guess. This pilot and demonstration project is funded with 8 million francs, which is maybe 10 to 12 Canadian dollars. And it will deliver market-ready technology. We work with industry partners here. We have first publications. You can scan the code. I present to you the first modeling results showing an efficiency between 70 and 100%. And the first experiments will start in December. If you have any questions, I'm happy to answer them. You can watch the whole video of the tunnel. If you want to experience an excursion into the tunnel, just scan this code and watch the video in full length. We thank our partners and Energi Simulation to be part of this project. Thank you.
Thank you, Dr. Brehme. Is Rick behind me? Dr. Chalaturnik, any questions? Okay, no question from him. Wow, thank you so much for actually bringing a real-life example and how you're doing this piloting. And in fact, heat storage was talked about quite a bit during the World Geothermal Congress in 2023 September in Beijing.
Yes.
So it is becoming an important energy storage and extraction scheme. So I guess the thing is economic of it. You have this tunnel and everything, and ultimately, when you drill from the surface and do all this, is it economic at this point in time in a similar type of geological setting?
In the low temperature setting, of course it will not. As long as you're below 100%, it's economically not feasible, I would say, right? We go to the tunnel because we know the reservoir. We can live monitor what we are doing. And it's the first time that this technology is used in fractured rocks. So we have to be careful. We have to go one step after the other. So we first go to the non-economic viable place to test the technology, to test our equipment, to test the general idea. Is it possible to transfer this from porous to fractured rock? And after that, we go to a real case scenario.
Okay. So is this like the Forge project in Utah where they share the data? Is this data public for? Okay.
The data is public, will be public. All the data is available. The Bedretto lab is an open lab, so if you're interested to work in the lab, just approach us. We charge a small amount for infrastructure and people because we have permanent technicians working in the lab. It's open every day. They work at weekends. So we charge a small amount to cover these infrastructure costs. But beside that, it's open for anyone who is interested to work in this lab.
Okay. All right. No questions on the floor, no online. So we'll let you go. Thanks again for